Let's talk about this counting choices probability packet. There are several different things that we're going to cover in here, including some things that we covered already with our activity manuals that we're going to do. We may stop in the middle or toward the end and take some notes on permutations and combinations as well, so just be prepared for that. As always, take a first look at this, see what you can figure out on your own, and then come back and we will talk about the correct answers. So pause the video, try to work your way through this first page of the packet, and then come back to look to see if my answers agree with your answers. All right, on this first page with counting choices, this is what we talked about with our fundamental counting principle in the activities manual video. I have answers for you here. Usually everyone gets A. B is a little confusing. I want you to think through this. If you have 5 pairs of socks, right? How many socks are in your drawer? Well, there's 10 socks. So I want you to visualize yourself with your 10 socks. You're going to pick one up. So you have a sock in your hand. You hold your sock in your hand, okay? You got your sock in your hand. I have my red sock. Well, how many socks are left in my drawer? There's 9 because I have the 10th one in my hand, and the sock I have in my hand is red. Out of the ones that are left, how many match this red sock? Just 1. So 1/9, my probability of picking a match if I pick another sock is 1 out of 9. The probability of getting one that doesn't match is 8 out of 9. Okay? All right. C is also a little bit squirrely. You may get there a little bit differently than I did and still got the correct answer. I'll talk you through my reasoning process. 3 out of 5 of your matched pairs of socks go with all of your shirt pant combinations, and the other 2 pairs only go with half of them. How often would you choose socks that don't match? Well, my shirts and pants, I've got 12 shirts, 8 pairs of pants. So that's how many shirt pant combinations I have. 2 pairs of socks only go with half of those combinations. That's what's going on here. 2 pairs of socks only go with half of these shirt pant combinations. So first I'm figuring out how many are half of my shirt pant combinations, and then I multiply that times my 2 pairs of socks that don't work. So 96 times I'm going to get socks that don't match. How many total combinations do I have? Well, I had 960. So 96 out of those 960 have the wrong socks. So 1/10 of the days I won't have socks that match. D, answers vary. There is no one way to get a right answer to that. My favorite answer is granimals. I don't know if any of you remember granimals, but they are all mixed and matched. Everything goes with everything else. Maybe a uniform, people say get a uniform so that you just have one color or everything always matches. Anyway, number 2, meal choices, fundamental counting principle. And then we kind of narrow it down. You only like 3 of the 5 sandwiches, 1 type of drink, and all 3 kinds of potatoes. That means there are 9 different meals that you actually like everything of out of the 60 possible meals. If I reduce that 9 over 60, turn it into a decimal, the probability that I will get a meal I like is 9 out of 60 would be 3 out of 30, or that doesn't work. I just did that wrong. 3 out of 20. 3 out of 20, or 15%. Notice that I can write my probability as a fraction, as a decimal, or as a percentage. Okay, let's look at the next page. So for this next page, let me come back over here. For this next page, we're talking about independent and not independent events with the multiplication rule. We already addressed independent and not independent events when we did the page with the cards and we looked at the intersection. If there's an intersection, the events are not independent. Events are independent, they are independent when one result is not influenced by another. For example, If I'm flipping a coin, oh, that's one of my examples there. Okay, so let's look at that. A, flipping a coin and getting heads, then flipping a coin again and getting tails. Does whether or not I get heads on the first flip actually influence whether or not I get heads or tails on the second flip? Well, no, these are independent events. Because every time I pick up that coin to flip it, the coin doesn't know what happened the first flip, the flip right before. It's just we're gonna flip it again. What about rolling doubles with 2 dice and then rolling doubles again? So I'm playing a game. I roll my doubles. I pick up my dice to roll again. I'm playing Monopoly maybe. So I pick up to roll again and I roll doubles again. Does rolling doubles the first time make it less likely I will roll doubles the second time? No, it really doesn't. They're independent events. Now, we know statistically that that we don't get many doubles. It's not a big possibility, a lot of possibilities for doubles in my sample space. But every time I pick up those dice to roll, I'm starting all over fresh. So each event is independent. C, drawing and removing 2 aces from a deck of cards and then drawing 2 kings. Are these 2 events, these 2 draws, independent? Well, no, they are not. They're not independent, and it's because of this and removing bit. For the first draw, when I draw my 2 aces, I had 52 cards to choose from. How many cards do I have for my second draw? Just 50. Since I have 2 fewer cards, because I drew 2 and I didn't put them back, I have a greater probability on the second draw of getting kings. Let's think about this. For the first draw, I have 4 kings out of 52 cards. What about for the second draw? Well, I drew aces, so I still have 4 kings in the deck. Now I just have 50 cards. So if you don't see that, put it into decimal form and compare the 2 decimals to see that when my denominator gets smaller like that, that means each piece of the numerator has greater importance. It has a higher probability. What about D? Independent or not independent? Well, we got that key word there again, removing. So these are not independent draws. Drawing and removing a red ball from a bag that initially contained 2 red and 3 white, then drawing a white ball. Well, my first draw again, how many balls did I have? I had 2 and 3 is 5. 2 of them are red. Well, I only had, 3 of them were white. So if I wanted to draw a white ball, I had 3 out of 5 that were white at the first draw. But then I drew one and I took it out and I left it out and it was red. So now there's just 4 left for me to draw from. I'm sorry. There were just 4 left for me to draw from. And out of those 4, 3 of them are red. Excuse me. 3 of them are white out of the 4 that are left. So the chances of drawing this white ball on the second draw are better than the chance of me drawing it on the first because I drew one of the other colors and kept it out. That and removing without replacement is what makes the 2 events independent. All right, let's look at the next page. This next page talks about independent events and the multiplication rule. So go ahead and work your way through this as best you can. Make sure you read the instructions. If they're not independent, you just write not independent. If they are independent, however, you use the multiplication rule to find the probability. We just learned the multiplication rule in our activity manual packet when we were doing those probability tree diagrams, and we multiplied the 2 probabilities together to get that probability of, for example, getting green and then blue or blue and then blue. That's our multiplication rule. Okay, for these, only the first one is not independent. Let's talk about why. Randomly choosing one person who's over 6 feet tall and weighs more than 250 pounds from a group of 100 people. Now, we have a crowd, It's not appropriate right now, but we have a crowd of 100 people. And we want to know what our chances are of picking someone who's tall and weighs more than 250, who's 6 feet tall or taller, weighs more than, or over 6 feet tall, weighs 250, amongst these 100 people. We know how many people are tall enough to be interesting to us. There are 13. And we know how many people weigh enough to be interesting to us. There are 8 people who meet our weight requirement. So there are 13 people who meet our height requirement. There are 8 people who meet our weight requirement. Why can't I tell you the probability of picking a person who's that tall and weighs that much? Well, because those are not independent of each other. In fact, the taller we are, the more we are naturally going to weigh because of bone mass and muscle mass. There's more of us by necessity when we're taller. So I'm going to be more likely to find someone who's 6'6" and weighs more than 250 than I am to find someone who's 5 feet tall and weighs 250. It's going to happen either way, but I see more people who are taller who weigh more just because that's what happens when you add bones and muscles. Okay, because of that, that means I don't have a total of 21 people to consider, because I guarantee that some of these people who are tall enough also weigh enough. So I don't have 21 different people here. Think back to our class. I always make people stand up for this. I could say something like, raise your hand if you have brown hair, and then say, raise your hand if you're wearing glasses. Well, I guarantee that some people are both have brown hair and wear glasses. So I can't just count the number of people who have brown hair, count the number of people who are wearing glasses, and know the probability of those things. They are not independent events. Our other 3 events on this page, however, are independent, and we can calculate the probability using our multiplication rule. Hopefully you work this out, rolling a 6 on one die, getting another 6 when I re-roll. So the probability of A then B, I'm going to use my multiplication rule. The probability of rolling a 6 the first time is 1 out of 6, because that's how many sides of the die have a 6. The probability of rolling a 6 the second time, still 1 out of 6, because there's still a 6 on one side of my die. So the probability of those 2 things happening consecutively is 1 out of 36. All right, probability of drawing an ace from a normal deck of cards. So that would be 4 out of 52 or 1 out of 13. Replacing the card, that's what makes it independent. Reshuffling and drawing an ace again. Well, again, I have the same number of cards, so I can either do 4 out of 52 times 4 out of 52 and reduce that, or I could do 1 out of 13 times 1 out of 13, and it's already reduced. Okay, 2 separate machines, separate. Each 99% reliable, which means I have a probability, 1% probability of breaking down, both breaking down. Now this happens all the time on campus. We have 2 copy machines available to us in the math department lounge. They are not hooked up to each other. They are separate machines. And so the probability of one being broken down shouldn't affect the probability, doesn't affect the probability of the other one being broken down. What's more likely to affect it is how much I need to copy things. That's not true. Okay, so I'm not looking at how reliable they are. I'm looking at how unreliable they are. The probability of them both breaking down. Well, the probability of the first one breaking down is 1%, or 0.01 as a decimal. The probability of the second one breaking down is also 0.01 because they're separate machines. They are independent of each other. So the probability of both of them breaking down at the same time is 0.0001, or 1/100th of a percent. We're going to answer it as a percentage because it was given to us as a percentage. Okay. When we start looking at factorials on the next page is where we start getting ready to talk about permutations and combinations. Yeah, okay, we're just going to keep going with what we've got. Let's look at factorials on the next page. Sorry, I'm still getting used to doing this thing over videos for you guys. In exclamation point is read as in factorial. It means to multiply all the integers together to get the result. For example, 5 factorial is 5 times 4 times 3 times 2 times 1. 3 factorial, I would start with 3. And there's that example right there, 3 factorial. 3 factorial would be 3 times 2 times 1, which is 6. Now, it defines for us 0 factorial. Here's why 0 factorial is defined as 1. I use factorials when I'm doing ways to group things with permutations and combinations that we're going to talk about soon. And if I have 0 things, how many different ways can I arrange 0 things? Well, just one way. There's just one way to have nothing. So that's kind of why we set it equal to 1. There's a more mathematical definition, but hopefully that will help you remember. 0 factorial is defined as 1. 1 factorial is just 1. That should make sense. And then 2 factorial is 2 times 1, which is just 2. We did 3 factorial. You guys do 6, 9, 10, and 11 factorial. Now, probably by the time you get to 9 factorial, you're kind of tired of pushing buttons. But you can do it, right? 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2. Let me show you a magic thing on your calculator. Okay, so when you have your calculator, you will have a probability button right here. If I want to do, for example, 9 factorial, I'm going to type my 9 and then push my probability button and move over to my factorial. So I move over there and say enter, whoops, and I have my 9 factorial and it gives me my result, which is a great way to check yourself, right? So go ahead and do 10 and 11 factorials. Notice that 10 factorial is just 9 factorial times 10. Yep, 0, 0. And then 10 factorial or 11 factorial would be 10 factorial times 11. Okay. Now we're going to evaluate and simplify some factorial expressions. When you get down in here, you're going to start seeing that there's some things that your calculator just can't handle. For example, on D and C both, I have 100 factorial. Well, if I do 100 factorial, thank heavens I don't have to enter all of those in, my calculator gets upset. It has overflow error. That number is too big to calculate with my calculator. I mean, it could calculate it, but it can't show it. So we need to think about how we can simplify these expressions without depending on our calculator so much. Now, be expectant that on the test, I'm going to ask you to simplify some factorials and show me how you simplify. So just be prepared for that. Okay, I'm making a note of that right now. Simplifying factorials. For example, 6 factorial divided by 7 factorial. Well, you know what both of these look like. 6 factorial starts at 6 and goes down to 1. My denominator is 5 factorial. It starts at 5 and goes down to 1. All of these things are being multiplied together. Do you see common factors? Well, yeah, I hope so. You got 5 over 5 is 1, 4 over 4, 3 over 3, 2 over 2, 1 over 1. So the result is just 6. You want me to make this even easier? Look at it this way. Instead of writing out all of your factors, if you're comfortable with it, you can look and see, okay, I'm dividing out 5 factorial. So oh dear. Sorry guys, I just lost my cardboard box setup for my stand for my Surface Pro. The very first week of this home stuff, I dropped my Surface Pro, and so now it's got this beautiful, beautiful corner, but it still works, and I caught it that time, so we're good. Okay, my heart's beating faster. Now, back to where we were. I have trouble fitting my hands between the two boxes and getting as much space as I want. Okay, I've got 6 factorial over 5 factorial. So I know my denominator is 5 factorial, correct? Well, my numerator is 6 factorial, which is the same thing as 6 times 5 factorial. Just like up here, 10 factorial is the same thing as 9 factorial times 10. And 11 factorial is the same thing as 10 factorial times 11. So I can stop at the biggest factorial that matches. You see that that matches? 5 factorial is that list of factors over that list of factors. I don't have to write them all out. I can just say, look, my numerator is 6 times 5 factorial. My denominator is 5 factorial. That's 1. And all I have is 6. Okay, let's look at B and see how we can simplify B. Well, I have 16 factorial in my numerator. My denominator, I have 2 factorial times 14 factorial. So let's simplify. I know in my denominator I have 2 factorial, which is just 2 times 1, right? Anything times 1 is itself, so I don't have to rewrite that 1. Times 14 factorial. So that's the biggest factorial. That's where I can stop. My numerator needs to start at 16. So I have 16 times 15, and then I can stop there at 14 factorial. The 14 factorials cancel out, and I have the option of either doing 16 times 15 and dividing by 2, or going ahead and saying, you know what, 16 divided by 2 is 8. So what I really have is 8 times 15. Either way, I get a total product quotient of 120. So I know you can do this one with your calculator. I want to be able to see that you know how to simplify it without your calculator. Right here on C, I already told you 100 factorial gives you an overflow error. Your calculator's not going to work for that. How can you do it without your calculator? Well, you just simplify. 100 factorial is the same thing as 100 times 99 factorial, and that 99 factorial factors out. You guys work on D, E, and F. See what you get. For D, you should get 4,950. For E, you should get 30,240. And for F, you should get 35. E is pretty simple. You can do that using your calculator or just multiplying it all out. 7 factorial times 3 factorial. So you have 7 all the way down to 1 times 3 times 2 times 1. Gets you that 30,240. My simplifying here on D, I would have in my denominator 2 factorial, which is just 2 times 1, times 98 factorial. My numerator starts at 100, and I can stop at that 98 factorial. So that all cancels. And then I can either multiply and get 9,900 divided by 2, or I could say, you know what, that's just 50. So I have 50 times 99. And then my final one, F, would be, okay, my denominator, I always look at it first. I've got 4 factorial. That's the biggest one. That's where I'm going to stop in my numerator. I also have 3 factorial. 3 factorial is 3 times 2 times 1. I usually get lazy and don't write the times 1. My numerator is 7 times 6 times 5 times 4, 3, 2, 1, which is that 4 factorial. That 4 factorial cancels. What I have left is the 765 and then the 3 factorial in my denominator. Well, 3 times 2 is 6, which leaves me with 35. All right, let's look at the next page. Ways to seek guests. This is where we introduce the concept of permutations. All right, hopefully you have already worked your way through this, and I am just reviewing to see if you got it right. We have 5 people at dinner. guess A, B, C, D, and E. They have names. Oh, no. I'm so sorry. Just ignore that. I got ahead of myself. So we're going to seat them. We've got 5 people and 5 seats. They don't have to sit that way. That's one way they could sit, but they don't have to sit that way. So let's think about it. If I invite them in and I say, okay, who wants to sit here in seat A? Well, there are 5 different people who could choose to sit in A. Let's say it happens this way. Let's say Tom sits in A. And then I say, okay, here's seat B. Who wants to sit here? And Ava says, I'm going to sit there. Well, Tom already sat down, so there were 4 people who got to fight over seat B. And then Ava sits down. There are 3 people left to decide who's going to sit in seat C. Sal sits down. Then these 2 are left, and they have to pick. One of them gets D, and there's only one person left to sit in seat E. If I count it down using fundamental counting principle, I've got 5 chairs. 1, 2, 3, 4, 5. 5 people can fit in can choose amongst themselves for the first chair. Then I've got 4 people who can be seated in the second. Then there's just 3 people left. Then there's just 2 people left, and then there's just 1 person left. Well, what does that look like? That looks a whole lot like 5 factorial. So when I start and count my way all the way down, my factorials, my factorials link to my fundamental counting principle, which links to my permutations. Now, how many ways can you arrange 5 people and 5 seats? Well, 5 times 4 times 3 times 2 times 1, 5 factorial, there's 120 different ways. What if I added another person in another seat? What if I have 6 people in 6 seats? Well, it's 6 times 5 factorial, which comes out to be 720 different ways. Now with permutations, order matters. With permutations, order matters. It's going to matter which seat I sit in with a permutation. What's another situation where order matters? Another situation where order matters would be like officer elections. President and secretary are different jobs. Order matters. If I'm getting picked for a prize, first prize is $1,000, second prize is $500. Well, order matters. It matters whether I'm picked first or second. Combinations, though, order doesn't matter. So look at that next page. See what you can do with it, and then we will talk our way through it. All right, so we want to choose a lunch combo. Our requirement is that we pick 2 different items, not the same item twice. So 2 different items each day. There's 6 things to choose from, and you want a different combination each day. How many items are available to choose from for item A? Well, item A, let's say we pick soft tacos. There were 6 things to choose from, right? Now that I've picked one, though, there's only 5 things left to choose from when I pick my B item for that day. I like rice. Let's pick rice to go with my soft taco. How could I calculate the total number of ways to fill those circles A and B? Well, I've got 6 ways to pick the first item, 5 ways to pick the second item, for a total of 30 different ways. I'm not concerned about the order of A and B, though. So taco burrito is the same combination. It goes on the same plate as burrito taco. That's only one possible lunch, not 2 different possibilities. If I do it that way, how many different combinations are there? Well, since I'm eliminating order and the order of the 2 things doesn't matter, I'm taking out half of those choices as being really not different, because soft taco rice is the exact same meal as rice soft taco. So that gives me 15 different combinations. And yes, there would be enough for 3 weeks of lunches, because they said we're doing Monday through Friday. So that's just 5 days a week for 3 weeks. I only need 15 different lunches. So yes, that works. With combinations, order does not matter. Now we're going to stop and take some notes before we do this last couple of pages. So grab a sheet of paper, and we're going to talk through some permutations and combinations and how they work differently. Now, if you've done a statistics class before, you're going to notice that I do not super emphasize the the statistical definition of permutations and combinations. I kind of do a Campbellized version. Makes them a little simpler. Hopefully, I think that it makes it a little simpler. And I'm going to cheat also with taking my notes, giving you guys notes. I'm going to give you some examples to have, and so you can look at these things. And we're going to compare numbers of permutations versus numbers of combinations. So with permutations, order matters. I have more possibilities. For example, if thinking about that meal example, if I consider taco rice different than rice taco, I have 30 different options instead of just 15. With combinations, order does not matter, so I divide out the duplicates. It's the difference between electing officers and just electing representatives. If I have 3 officers for the club, president, vice president, secretary, those jobs are different. If I'm selecting 3 student government representatives, they all have the same job. It doesn't matter which one picked first because you're still one of the student government representatives. You have the same job as the other 2. So I don't have as many combinations as I do permutations. Mathematically, my definition for permutation, NPR, where N is the number of possibilities and R tells me how many of them I pick. So I set up my permutation formula as N factorial over N minus R factorial. Now I'm going to show you how this works according to the definition and then show you my shortcut. Remember, we just did this, so hopefully you remember 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120. Okay, let's say I have 5 people in the club who are running for office, and I need to pick 3 of them as officers. So order matters. It's a permutation. By my definition, I do N factorial in my numerator. I have 5 total people running, so that's 5 factorial. My denominator is N minus R factorial. So 5 pick 3, 5 minus 3 is 2 factorial as my denominator. So I have 5 factorial over 2 factorial, and I show you how I simplify. I end up with 5 times 4 times 3, which is 60. Here's the shorthand version of permutations. I have 5, I need to pick 3. Since I have 5, that's my starting place. Once I've picked one, there's only 4 left to pick from, and then I pick one again, and there's only 3 left to pick from. 5 times 4 times 3 is 60. So my shorthand version of permutations kind of cuts out that denominator. I look to see how many I start with, and then how many times I pick. For example, here's 3 more examples. 7 pick 4. I start with 7, and I have 4 blanks to fill. 7, 6, 5, 4, because I pick 4. 10 pick 3. I'm going to start with 10. I have 3 blanks to fill. I showed you how to work it out according to the formula, but what it ends up being is just 10 times 9 times 8. Start with 10, pick 3 times. That gives me 720. But what if I get down here to something like 45 pick 6? Well, even if I do it my shorthand way, I've still got to do 6 blanks to fill, and then I've got to start with 45. So 45 times 44 times 43 times 42 times 41 times 40, and that gives me 6 different opportunities to miskey something in my calculator. Let's go back to that probability button. Remember our probability button right there? Let's clear out my overflow error. Okay, so type in how many you're starting with. We've got 45 in this case. Go back to your probability button and look right there, permutations. So I hit enter and it loads that into my calculator. So I've got 45, pick, and then I need to tell it how many times to pick. We're going to pick 6. 45 pick 6 gives me the same result as if I did that multiplication the long way. If you want to make sure you know how you're doing, if you're doing it correctly, do some simpler problems, 7 pick 4 that you already have the answer to, and make sure that you're doing it the right way. Let's compare permutations now to combinations. Remember, permutations order matters. Combinations order doesn't matter. So I start with the number of permutations, but then I divide out the duplicates. So I'm going to start by thinking of my permutation formula. Remember this permutation formula? Right there? But then I divide out the duplicates. Permutation formula, then divide out the duplicates. This is how I divide out the duplicates. So if I have 5 combinations of 3, 5 choose 3, I start with my number of permutations, and then I divide by r factorial. So with my formula, this is what I start with. There's my permutations part, and then I'd use that 3 factorial, r factorial, also in the denominator. So I have my 5 times 4 times 3 that I already had, but then I have to divide by 3 times 2 times 1. And instead of, go back to your other page of notes, 5 permutations of 3, we got 60. I divide that by the number of duplicates by 3 factorial. 3 factorial is 3 times 2 times 1. 60 divided by 6 is 10. Okay, check out, we already found 7 permutations of 4, 10 permutations of 3, and 45 permutations of 6. I want you to go back now and do those with combinations instead, where order doesn't matter. So I think about finding the number of permutations and then dividing out the repeats by doing that r factorial in the denominator. 7 pick 4 would be 7 times 6 times 5 times 4. Divide out the repeats. 10 pick 3, 10 times 9 times 8. Divide out the repeats. And then for 45 combinations of 6, I start with my 45 pick 6, and then I divide out the repeats with 6 factorial and get this. But I'm sure by now all of you are going, you know what? I think I saw that probability button as well. You did. Go back to your probability button, move over 1 time, and you've got combinations. And it does it for you. Remember that I am going to ask you to simplify some things when you get to the exam. Like when we did factorials, I want you to know how to simplify those things. But having a calculator that you know how to operate is excellent too. All right, so this page, ways to choose lunch combinations. I want you to pause the video, work on that, and then look back to see if you got things correct. And I am just going to magically show you the correct answers. All right, hopefully there are no questions from that. You know the difference between permutations and combinations, and you know how to calculate them both now. So let's think about this last page. We've got a word scramble, and I'm going to just be honest with you. I had a horrible time answering the bottom of the word scramble, but the top part of this page is really good stuff. It encourages you to do an ordered list, or you could do, tree diagram would be too big. You need to recognize that you're going to come up with 24 possibilities. And then you figure out how many of those 24 are actual words. Work through this. I'm just going to show you the key again. Work through this and then look back at the key. Let me see if I can get all of that in. It's way more fun when you work it out on your own first, rather than just following along.